In our discussion of motion in one spatial dimension, I want to take some time to focus on a limiting special case that is nonetheless uh, broad and generally useful. It's actually just a really good way to develop some of your physics intuition. This is the special case of motion where the acceleration is constant, and that constant could be zero. So in that case, the velocity is also constant. Um, the statement that the acceleration holds a constant value and does not change means that we are in the regime of kinematics. It may not seem like motion with a constant acceleration is all that general, but for most of our everyday activities, we are on the surface of the Earth. The acceleration due to Earth's gravity is roughly constant. So as long as over the span of motion we're interested in the effects of air resistance and air drag and other forces along those lines are insignificant, then you are in the regime of motion with constant acceleration. So most all of your sports ball games you can think of: basketball, football, baseball, softball, tennis, golf, da 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 da. To a good first approximation, that is motion with a constant acceleration. All right. In that case, when we are dealing with kinematics, we are essentially playing a game. We have, as we will see, 5 equations available to us, and there are 7 variables. So you can basically think of this as doing something like Sudoku. There are things that will be specified within the problem, things that are unknown, and you have up to 5 equations to pick to utilize to solve for the unknown quantities. To step through what the kinematics variables are, t means the final time, whatever you want to pick the final time to be. T naught is the initial time, and by default your textbook takes that to be 0. So you start your stopwatch at time t equals 0. X is the position of the particle at the final time. So where is the particle when the time is t? X naught is the position of the particle when time is 0, so the initial position. V is the velocity of the particle at the final time. V naught is the velocity of the particle at the initial time, so when time is equal to 0. And there is only one variable for the acceleration because the acceleration is constant. So we don't have to differentiate between the final and the initial acceleration. When we are talking about motion where the only relevant force is the force of gravity, that means we are talking about free fall. If we take your book's convention where up is the positive direction, then the acceleration for free fall on Earth is going to be a is equal to minus lowercase g, and that g stands for 9.81 meters per second squared, the acceleration due to Earth's gravitational field at the surface of the Earth. 9.81 is an average over the surface of the Earth. It actually varies a bit from place to place. That's one thing we'll perhaps learn from lab, is what the value of the acceleration due to gravity is at your location. All right, so 7 possible variables. The tools to use are 5 equations of kinematics. We have an equation that says that the final velocity is the initial velocity plus acceleration times time. You'll note that equation does not involve position. We have an equation that gives us a displacement is the initial velocity times time plus a half acceleration times squared. So position is changing quadratically with time. This one does not involve the final velocity, but it has a partner equation here at the end. Displacement and position is equal to final velocity times time minus a half acceleration time squared. So this one does not involve the initial velocity. We have an equation that is basically arising out of the average velocity. A half of the quantity final plus initial velocity is the average velocity. Because the acceleration is constant, the velocity can change only linearly. And this is basically saying that the displacement is the average velocity times time. We have one last equation of kinematics. It may not be obvious at first. I have a little video going through the derivation of all 5 of these. This equation is exceedingly useful because it does not involve time. You have the final speed squared minus the initial speed squared has to be twice the acceleration times the displacement. And this will generalize to more spatial dimensions as well. So given a problem in kinematics, you have up to 7 variables that you are going to want to make an inventory of, and you have 5 tools at your disposal, 5 equations of kinematics. And the way you play the game is you want to pick the equation of kinematics that has only one unknown and everything else is known, and just sort of observe which is going to be a good equation of kinematics to use by which variable is missing from that kinematics equation. So our third equation has no time, our top equation has no displacement, so forth and so on.